doctors, and the research facilities. I was so excited that I didn't see it, but I like met all of them.
All right, guys, let's go ahead and get this quiz out of the way. Probably don't want it. Okay.
Yeah. Thank you.
Next one. Everybody got one? All right. Oh, okay. Sorry. All right, guys, just give it 2 more minutes. one more minute. All right, guys, let's go ahead and wrap them up. Do I need to come up? Do they still have theirs? Cool. So I don't have to waste a trip upstairs. All right. All right, in just a second here, we're going to get pick up where we left off the other day. Just a quick note. I know several of you have unfortunately had to miss a few periods here and there because of COVID, quarantine, school trips, whatever else. If you still need to make up a quiz or an exam that you missed, please get in touch with me pretty soon, because we want to go ahead and make sure to not let that get too far down the road. We don't want those to be sort of hanging over our head as we go along. So let's make sure to go ahead and get those scheduled. All right. Okay, so we're going to pick up where we left off. We had just started talking a little bit about the Diels-Alder reaction. And if y'all remember, Diels-Alder reaction is basically a reaction between a conjugated diene and then something called a dienophile. And dienophile is just something that basically contains an alkene. Right? And we saw a couple of features about the dienophile and the diene that can affect reactivity. How does it actually work? Well, let's take a look at an example. Right? This is the simplest Diels-Alder reaction that you can possibly have. Notice it's got the simplest conjugated diene, and it's got the simplest dienophile. Right? And I drew them like that just so the mechanism's a little bit easier to see. Right? I've already got the diene drawn in the S-cis conformation. Remember, it's constantly spinning, but this is where it's going to be reacting. Right? And we learned that other than these two species, all you got to have is heat. Right? So basically what's going to happen here is you see a bunch of pi electrons. Right? You see 3 pi bonds amongst the two reacting molecules. These are sort of going to start moving around in a little merry-go-round of electrons. Right? This pair of electrons will come over here and make a bond between this carbon and this carbon. This pair of electrons will move over here and make a bond between these 2 carbons. And this pair of electrons will hop down and form a pi bond between those 2 carbons. That is the universal Diels-Alder mechanism. Right? Completely concerted. All of this happens at one time. Right? The other day we said that we could make a general prediction about the final product of a Diels-Alder reaction. What do we always end up making? A new 6-membered ring. And that's what we have here. That would be our product. Right? In this process, no matter which Diels-Alder reaction you have, it's always concerted. And also, you see this pattern. You see the breaking of 3 pi bonds. Right? You have 3 pi bonds at the beginning. They all shift around. And they all break. And you also form 2 new sigma bonds and 1 new pi bond. And you can see here, here's the 2 new sigma bonds that you made here. And here's the new pi bond that you made right there. Okay? That's one thing that's kind of nice about Diels-Alder reactions is, you know, from a mechanism standpoint, they're very, very predictable. Okay, you just have to make sure that whatever your dyne is has been drawn in the S-cis conformation. One thing that people have a hard time with sometimes is keeping track of carbons. Like which carbons are going to be involved in the making of the sigma bond, which ones are going to be involved in the making of the pi bond. One thing that's kind of helpful sometimes is for you to sort of tag your carbons as you're going through this. Like I could call these carbons A, B, C, and D. I could call those X and Y. If I'm looking at them over here, that's how they end up. Bless you. Okay. So far, so good? Are there any questions about how we got that one? Let's try another one. Like I said, this is the simplest, you know, Diels-Alder reaction over here. You can have other stuff, of course, hanging off of your dyne and dienophile. Let's say we had this. Right? That one looks a little bit more complicated. And I guess it is, right? But it's going to work the same exact way. Right? So if you're approaching this, what are you going to do first? Yeah, you'll notice that dyne is currently in the S-trans configuration. You need it in the S-cis. So what you're going to have to do is you're going to have to mentally rotate around this single bond. That can take a little bit of practice. That's not the most important thing to do. But you need to get this in the S-cis configuration. I personally, and this is just a me thing, I personally like to stand it up on its side like that because I think it's easier to do the mechanism. You don't have to though. But yeah, if you're to take that and twist it around into the S-cis configuration, which is the conformation, then it would look like that. And then, you know, you have the dienophile. And again, it's just kind of nice to stand it on its side. Me personally, because it makes the mechanism easier to draw, I think. And then you're set up, right? You just delve into your little merry-go-round of electrons, right? To make your new 6-membered ring. This carbon is going to form a sigma bond here. This carbon will form a sigma bond here. So 4 of the carbons in the 6-membered ring always come from your dienophile. Excuse me, sorry, rewind. 4 of your carbons in your 6-membered ring always come from your diene. The other 2 always come from your dienophile. And voila, you get that. that make sense? Are there any questions about how we got that? All right, let's try another one. This one's a little bit more complicated in a very subtle way, so I'd be pretty impressed actually if you picked up on this initially, but we'll see. All right, so let's say we have this. We have that. Actually, no, sorry, I was looking at the wrong one. This. And we have this. All right. And your strategy, again, is going to be exactly the same. First, always make sure that your diene is in the S-sys configuration. And then you can react with your diene of 5. The exact same thing that you've done in the other examples, and boom, you got yourself a product. Does it make sense how we got to that? Any questions? All right, like I said, this one's a little bit more complicated than the last couple we've shown. Really pick up on why that is. Like I said, it's kind of subtle. Yeah. Yeah, I think I know what you're getting at. Basically, having this alignment, this setup produced this product, right? And you'll notice that this methyl group and this carboxylic acid group are opposite to each other, right? They're at the 1 and the 4 positions. Well, that's because I chose to draw it like this. What would happen? What would have happened instead if, you know, like when I drew the dienophile, what if I just stood it on its other end? Like that. How does that translate to the product? Where do I put the carboxylic acid group? Here. I still put it in the same place? Where would I put it? Down below, right? Is this the same product as the one I just drew? Guess what happened? Guess what you get? You get both of them. Unfortunately, there's no way we can just say, oh, the dienophile is going to stand like this. Yeah, it could be aligned in either direction. Either one of these is possible, certainly, and they both do happen. And that will result in the placement of the group in a different spot. With the other examples we went over, you had a symmetrical arrangement, so it ended up being the same regardless. But that is something that you kind of have to keep in mind as you're going through these. So, as a precaution, if you're doing one of these, you may want to try to sketch it out both ways. Kind of a hassle, but it really is kind of necessary in order to figure out if you're going to have a mixture of products. Okay. So, make sense? Questions? All right. Sometimes your dienophile has two substituents on it. One thing that you notice we haven't really talked about yet with these is, other than the S-cis S-trans stuff, is stereochemistry, right? We've been making stuff that has stereogenic centers. I'm not really too concerned about that at the moment. Instinctively, what do you think you would get stereochemically? I've just erased, but you know, you can look at your notes. Yes, racemic mix, because everything is planar, right? The dienophile is planar, the dienes are planar. So you could actually get a racemic mix. Not too worried about it right now. However, sometimes we can have more than one substituent. This is where we will want to be a little bit more stringent about stereochemistry. Let's say we have this. Well, our dienophile has a couple of ketone groups on it. Go through the little merry-go-round. Draw your six-membered ring. And you know that both of these carbons, they used to be part of your dienophile, they're going to have ketone groups too. Okay. Now, whenever we have a situation like this, we're going to be a little bit more concerned about the stereochemistry, because we need to represent whether these two groups are on the same side of the ring or on opposite sides of the ring. Cis or trans, in other words, right? Do you get a, all cis? Do you get all trans? Do you get a mixture? What? Good luck. Or good luck. Gosh, that sounded like a real asshole thing to say, didn't it? I didn't mean to say good luck. I meant to say luckily there is a way of thing. So no, I wasn't trying to. Oh Lord. Okay. Wednesdays are my hardest day. All right. So here's a rule. Stereochemistry of your dienophile is preserved. That is our guideline. Stereochemistry of your dienophile is preserved. That means if you had a cis arrangement in your dienophile, it's going to be cis in your product. If you had a trans arrangement in your dienophile, it's going to be trans. All right. What did you have in your dienophile? Cis or trans in this case? You had cis, right? So that means these guys are going to be on the same side. I could have also drawn those with two dashes instead of two wedges, but it ends up being the same. So this is a meso compound. Yeah. I've done this with trans. Sorry, I had to get that drawn. If we had done this with a trans dienophile, like in this case, we would have had a trans arrangement of our ketone groups. And in this one, you could actually draw two separate ones because there's no way these can superimpose. So in this one, you'd get two different stereoisomers, but they would both be in the trans arrangement. But yes, that's a very important rule. It's a very powerful rule. Always remember that stereochemical arrangement of your dienophile will be represented in the stereochemistry of your product. Okay. Does that make sense? Questions? All right. Here's one for you guys to work. Take a couple of minutes and see what you can do with this. What I really hate is when you're talking with a mask on and like one of the little strings from inside your mask gets in your mouth. Ever happened to you? It's really annoying. All right, looks like a lot of you have stopped working. That either means you got it or you have no idea what you're doing. Either way, let's take a look. All right, first thing I need to do, what?
Put it in that.
Yeah, we need that SS configuration, so I'll twist it around so we have SS, right? I'm going to stand this one on its side just because that's what I like to do. Radio-round of electrons. Make our new 6-membered ring. Now we just have to put the substituents on the right carbons, right? Got a methyl group there. We have a couple of ester groups on those respective carbons. Doesn't matter which way we stood this end to end, it's the same, so we end up with this. Tell me something about stereochemistry. Yep, stereochemistry is preserved, so these two ester groups are going to be cis. And there's a couple of different ways that you can represent this. With either dashes or wedges. I think those are different products. Yeah, those are different products. If you flip that one over and turn these to wedges, but then the methyl group would be in a different spot. So, all right. Any questions? Sound good? Are we a fan of the Diels-Alder reaction so far? Like, not as much as any other reaction. Diels-Alder reaction is actually pretty interesting. It's actually used quite a bit in several important biochemical reactions. All right, I'll tell you a little bit more about that in 1 second here after I introduce the next concept. Take a look at this one. Another Diels-Alder reaction. Well, this one's a little different, right? What's different about this one? Got a cyclic dienophile. Yeah. Haven't seen that yet. So, how does this affect things? Well, as far as the mechanism, it doesn't. Not at all. You still go about your business the same way that you did before. And you're still going to make a new 6-membered ring. Like that. Now, what does the rest of the molecule look like? You may wonder, okay, how do we represent all this other stuff? Well, here's a question. Did we break this ring at all? No, we didn't. It's still intact. This ring is still there, and it still uses these carbons, right here and here. The new 6-membered ring also uses these carbons. So what you end up with is a case where the two rings are fused together. That would be your product. So if you have a cyclic dienophile, you get what we call a fused bicyclic product. Kind of fancy schmancy sounding. Bicyclic means just two rings. Fused means they're joined together. There you go. Not any more difficult than the other reactions that we've done. It just looks more impressive. Have y'all talked much about, in your biology classes, have we talked much about steroids? A little bit. So, like, you know, steroid and steroid derivatives, cholesterol, testosterone, et cetera, et cetera. Once you take biochemistry, you guys have biochem, right? You guys probably talked about that quite a bit, didn't you? More than you really wanted to know. Yeah. If you look at the structure of a lot of steroids, they consist of many fused rings that are joined together. And a lot of these systems are made up either naturally or synthetically through Diels-Alder reactions. Yeah, so Diels-Alder reactions actually go on in living systems. One really cool application of this is the Japanese pufferfish. You see, you know what the pufferfish is? It, you know, gets scared and it goes all spiny and it's really, I really look stupid doing this. You know what a pufferfish is, though, right? Okay. Pufferfish are actually, they actually contain one of the most toxic poisons in the world. You may have heard of it if you're into Japanese cuisine. Ever heard of something called fugu? Ooh, what's fugu?
Isn't it like this like pouch that's like in the pufferfish? And
Well, fugu itself is as absence of the pouch, right? Fugu, if you go to like, there are certain Japanese places, and I have no idea if there are any nearby or not. You can check into it. There are certain Japanese restaurants that will serve fugu, that is Japanese pufferfish, right? But not just any place can serve this, because when you cut up the pufferfish, you have to be very, very careful. It contains like this little organ or pouch or something that contains an extremely toxic toxin. Yeah, it's hard to say. In fact, it's like, I think in like maybe like the top 5 most poisonous chemicals on Earth, something like that, extremely dangerous. And if you if the chef sort of nicks this pouch at all while it's preparing the pufferfish, that's it for whoever eats it, right? You're gonna die. That toxin is actually produced through a Diels-Alder reaction, so that's the connection there. It's not, you know, a positive connection if you're looking to eat pufferfish, but you know, there you go. Yeah, the chefs that serve fugu, they have to be specially trained. If you order it, it costs like a crap ton of money too, because, well, you see how skilled somebody has to be. Okay. Yes, all made possible because of the Diels-Alder reaction. All right. Got 2 minutes. How about if we have this? We got another cyclic species in our reactants, but it's not a cyclic dienophile this time. This is a conjugated cyclic diene. And this one's also going to produce a product that's going to look a little different as far as how we draw it. As far as reactivity, it works exactly the same as anything else we've been doing, right? Still get the little merry-go-round of electrons. And you do create a new 6-membered ring. Right. What is not included yet, though, in the product structure? Something missing. There's a carbon missing. Yeah, again, let's label these. We have A, B, C, and D, X and Y. A, B, C, D, X, and Y. So this is poor little carbon up there that's unaccounted for. We'll call him E. He didn't go anywhere. He's still there. In fact, E is still connected to both A and D at the same time. Right? We can represent that a couple of different ways. Here's the bad way. I won't say bad. Here's the less good way. All right. There's E right over there. E never came apart from the other carbons, right? But it's going to be located in a different plane than that new 6-membered ring. It's like one of those little mind tricks, right? If you can sort of eliminate this side over here and sort of look at just this part, you can see the 5-membered ring still there. It's just in a different plane. It's like you took part of that 5-membered ring and sort of folded it up, origami style or something. But it's still there. It's almost like this E forms a bridge, bridge between carbons A and D. If you have a cyclic diene, it forms something called a bridged bicyclic system. So cyclic dienophiles produce fused bicyclics. Cyclic dienes produce bridged bicyclics. I see we're almost out of time here. What I'm going to do is I'm going to draw the better way to draw this. You're going to totally hate it because everybody always does. But then we'll talk more about it on Friday. Just like that. Brings back some essences of chair conformations, but not quite. So keep this in your back pocket, and I will, like I said, I will go through this and talk more about it. I'll do examples on Friday. All right. Okay, just real quick before you guys leave, real soon, I'm gonna start trying to get you some lab reports back. I'm treating lab reports a little bit differently. I'm having my TAs help out with lab reports. So what they're going to do is they're going to go through and help identify some basic things I usually look for: grammar, spelling, punctuation, et cetera, and also the presence of certain discussion points. And so we will, on a weekly basis, kind of go through what I want them to look for in the lab reports. They're not going to put the grades on them. I'm still going to give you the numerical grades, but they're going to help me out a lot with the assessment of them, sort of getting them marked up. So whenever you share your lab report with me, what I'm going to do is I'm probably going to go ahead and further share that with either Alex or Skylar. So just in case you're wondering, why Alex or Skylar is like all of a sudden making notes on your lab report, that's why. All right, that's all I got. And then Alex and Skylar, we need to get together like in the next little bit, either by the end of this week or towards the beginning of next week, to kind of go over. Okay, Skylar, are you here Friday? Okay, I'm free on Friday anytime between like 9 and 2. So is that okay with you? Perfect. Yeah, Friday after class. Let's do it.